All right, guys, so we're going to be talking about fundamental trig identities today. So getting into some fun things. But first, just remember, what is an identity? An identity is a mathematical statement that is true for all values of the variables for which the statement is defined, meaning we don't have to define it ourselves, right? We could say like, if we have 1 over x, x could be anything except 0. So there should be some kind of defined set for the values we can input in for the variable. If not, it could be negative infinity to infinity, and we're all good. But anyway, so an identity basically means it's always going to be true, no matter what we plug in. I can plug in 5, I can plug in pi, as long as it's in that defined set of numbers I can plug in, it should work. So there are some identities that are written down here that are good to know, and some we actually already know. So a reciprocal identity is basically like, what is cosecant? Well, we know that's 1 over sine, right? Secant, 1 over cosine, cotangent, 1 over tangent. And we've talked about tangent and cotangent as well, right? Tangent is sine over cosine, and then cotangent is that reciprocal. So then we have a couple more identities we haven't talked about yet. There's the Pythagorean identity, which really relates to the Pythagorean theorem, which we all know and love, right? A squared plus b squared equals c squared. And here we're looking at basically the idea of cosine squared cosine squared theta plus sine squared theta equals 1, right? 1 plus tangent squared theta equals secant squared theta, cotangent squared theta plus 1 equals cosecant squared theta. You can memorize those, but if you're interested, you can totally look up how to derive them as well. And in our textbook, you can find the derivation of the Pythagorean identity. So I won't bore you with that here, but you can definitely look it up if you're interested. And it does relate back to that handy dandy Pythagorean theorem, that a squared plus b squared equals c squared. Then we have our negative angle identities. Sine of negative theta equals negative sine theta, cosine of negative theta equals cosine theta, and tangent of negative theta equals negative tangent theta. And these negative angle identities I think are pretty cool because we've already talked about the unit circle. So if you just look at your unit circle and look at, let's say, sine of pi over 6, which we'll get as 1/2. Then if you look at what is sine of negative pi over 6, which would be that reflection, so you'd actually be looking down at 11 pi over 6, we'll see that is negative 1/2. So the sign of the negative angle, the opposite angle, is the opposite value. So you can kind of see that relationship in the unit circle. So really the only thing that's kind of new here is the Pythagorean identity. And you can totally look up how those are derived if you're interested in it. But what we want to do is we want to be able to work with them to do a couple of things. So let's go ahead and jump into our first example, which is proving trigonometric identities. So how do we prove a trigonometric identity? What we're basically doing is we want to get both sides of the equation exactly the same. So we want to have matching expressions on both sides. So I want you to remember again, to prove the trig identity, what you're doing is you want both sides to match. So if you look at this first example where it says tangent theta equals secant theta over cosecant theta, there's no hard, fast rule that says, okay, you have to make that right side equal to tangent theta. You can totally transform tangent theta into secant theta over cosecant theta if you'd like. You just basically see what's easier for you. And you either want to aim to get tangent theta equals tangent theta, or secant theta over cosecant theta equals secant theta over cosecant theta. That's what I was trying to say earlier. So it doesn't matter to me. As long as you get the same thing, the exact same thing on both sides. We don't want to have a negative on one side and a positive on the other, right? It has to be exactly the same. Then we've proven it. So then what you'd want to do is reference your trig identities and transform one of your sides using the identity. So not using anything that's, kind of illegal and doesn't make mathematical sense, but we're going to transform one side to match the other. So when I look at this, I'm going to go ahead and look at secant theta and cosecant theta. So let me just scroll back up here. So you might notice, hey, secant theta is 1 over cosine theta. Cosecant theta is 1 over sine theta. So what I could do is I'm going to say, let's leave tangent alone. And like I said, do you have to leave tangent alone? No, you can play around with tangent if you like. But I'm going to say I want to leave tangent alone because I remember right away secant theta is 1 over cosine theta and cosecant theta is 1 over sine theta. So what I can do here is I can say, well, this secant theta over cosecant theta is the same thing as secant theta times 1 over cosecant theta. So that just helps me clarify my work. And let me kind of make this a little bit easier to read. There you go, just made my pen a little bit thinner, so hopefully that's a little easier to read. So then I'm going to go ahead and rewrite secant theta as 1 over cosine theta because that is totally a reciprocal identity. I'm not doing anything that's coming out of nowhere, right? I'm just using one of those identities. So then tangent theta equals 1 over cosine theta. And then I can do the same thing here. Cosecant theta is 1 over sine theta. So I'm going to make this 1 over sine theta. And we've done these fractions inside a fraction a lot, but remember that's 1 divided by 1 over sine theta. So we can do that fraction multiplication and we'll end up with, or fraction division, which turns into multiplication, when we'll end up with 1 over cosine theta times sine theta. Because remember, this is 1 divided by 1 over sine theta. And then you can do your fraction multiplication, or division, right? You're going to switch that division sign to multiplication and multiply by the reciprocal. So then I can say, okay, tangent theta is equal to sine theta over cosine theta. And what do you know? That's another identity. Right over here, tangent theta equals sine theta over cosine theta. So what I've just done is I've said tangent theta equals tangent theta. So there's the proof of that identity. So this is where it's kind of fun. You get to play around with these identities and see how things work. And if it didn't work to try to show tangent theta equals tangent theta, try keeping secant theta over cosecant theta and play around with tangent theta. So it's kind of up to you, which is kind of fun about these proofs. Okay, let's do one more proof, and then we'll look at one other type of problem here. So we have 1 minus cotangent theta equals 1 plus cotangent of negative theta. So again, you kind of choose, right, which one you want to manipulate and which side you might want to keep the same. And sometimes it actually would be helpful to manipulate both sides. It's up to you, right? Again, whatever you're more comfortable with. But I'm going to say, let's leave this 1 minus cotangent theta on its own because I see this negative theta, which makes me think, okay, I've got some negative angle identities. Let's work with that. But I don't see a negative identity for cotangent. So let me kind of erase what I've worked with here. I'm going to say, okay, well, where have I seen cotangent? Maybe I want to play with cotangent. Well, I don't have a cotangent squared, but I do see a plain old cotangent. So why don't we rewrite cotangent as cosine theta over sine theta? So I'm going to start here, 1 minus, oops, there you go, 1 minus cotangent theta, because I decided I'm going to leave this left side alone. I'm going to leave that there, and I'm going to change this cotangent into cosine of negative theta over sine of negative theta, right? So now we have some negative angle identities we can work with. We can see, hey, this, somehow that got erased. This cosine of negative theta is just cosine theta. The sine of negative theta is negative sine theta. So let's go ahead and substitute those in as well. So now 1 minus cotangent theta equals 1 plus normal cosine theta over negative sine of theta, right? And then positive divided by negative is a negative, so I can rewrite this as 1 minus cotangent theta equals 1 minus cosine theta over sine theta. And what do you know? This cosine theta over sine theta is once again cotangent. So 1 minus cotangent theta equals 1 minus cotangent theta. Two matching sides, we've proved that identity. Pretty cool. Okay, so we can also use these trigonometric identities to help us with other types of problems. So I think the proofs are probably the most fun, though that's probably because I'm a geometry teacher. But we can also rewrite these trigonometric expressions in terms of a specific trig function. So if you look at this direction, the set of directions, we are specifically asked to rewrite these expressions using cosine theta. Just cosine theta. So no sines, no secants, no cotangents, no tangents, just cosine. Okay? So then we still need to go back and look at our identities and think, okay, well, how do I transform this? So all I see is cosine. So then what I want to do is I want to think about how each of these trig functions that are in my expression relate to cosine. So if I'm looking at secant theta, I can remember, hey, secant theta equals 1 over cosine theta, right? And then you might be wondering, wait, this 1 minus sine squared theta, oh, what's the sine squared business? Well, that's when we go back and we look at our Pythagorean identity. Where do we see a sine and a cosine squared? In this very first one. This cosine squared theta plus sine squared theta equals 1. And just a side note here, this cosine squared is just basically like an x squared, so it's just that cosine value squared. But anyway, oops. I scrolled down too far. So we can remember, hey, cosine squared theta plus sine squared theta equals 1. I don't want sine, I want cosine. So let's take away let's take away cosine squared so we can get what sine squared equals, and then I can substitute that in. So I'm just manipulating this equation so then I can basically substitute an equivalent expression. So sine squared theta equals 1 minus cosine squared theta. So what I want to do is I'm going to take each of these, right? This 1 minus cosine theta, this 1 over cosine theta, and plug it in to that original expression. So I'm going to replace secant theta with 1 over cosine theta. So that's secant. Then I'm going to replace 1 minus sine squared theta with 1 minus parentheses 1 minus cosine squared theta. And then I can simplify this. So always simplify as much as you can. All right. So I'm going to leave this 1 over cosine theta on its own because I want to do my PEMDAS, do the parentheses first, whatever I can in here. Distribute this negative. So that becomes 1 minus 1 plus cosine squared theta. So then I'm going to get 1 over cosine theta equals, that cancels out to become 0, or not equals, excuse me. I'm going to get 1 over cosine theta, and then the 1 minus 1 turns into 0, so it's going to be times cosine squared theta. So that's equal to cosine squared theta over cosine theta. And like I said, imagine that cosine squared theta is just an x squared. So how would you simplify x squared over x? Well, we can get rid of one of them, right? So this reduces down to, it simplifies down to cosine theta. Okay, one more. So sine theta times cosine theta, and then times the quantity tangent theta plus cotangent theta. Again, we don't want anything but cosine. So what do we do? Well, what I did here was I went ahead and I distributed. So I said, okay, let's take these, the sine theta times cosine theta and multiply it out. So I ended up with sine theta, cosine theta times tangent theta plus sine theta, cosine theta times cotangent theta. Let me rewrite that a little bit neater. Sorry about that. All right, so again, sine theta, cosine theta, cotangent theta times cotangent theta. And then we can remember, hey, don't forget, tangent is sine over cosine. Cotangent is cosine over sine. So let's simplify some more. So I can simplify by first substituting in sine theta over cosine theta for tangent. And then, same deal, substitute in cosine theta over sine theta for cotangent theta. I'll move this over a bit. And the point of that is now I can simplify because we can see, hey, look, there's a cosine in the denominator, cosine here. Let's simplify that down to 1, right? I have a sine times a sine in the denominator. That also simplifies down to 1. So I'm going to end up with sine theta times sine theta plus cosine theta times cosine theta. And remember, this is just like x times x, y times y. So this is sine squared theta plus, well, let me rewrite that, sine squared theta plus cosine squared theta. And if we look back, where have we seen this before? Right here. In the one I've circled right up here, right? I'll highlight it again. Cosine squared theta plus sine squared theta equals 1. So it's okay that we don't have a cosine anymore because we simplified that all the way down to 1. And there we go. That's a simplified expression. Okay, so that's it for today's lesson, which is really just a bunch of examples on how we can use these trig identities. And of course, there's lots of different problems, so please interact with those identities. There are a few you-try problems for you guys to try if you would like. There will be a separate video going over those answers. So again, those you-try problems are optional, but if you'd like to go over them, please watch the next video. And as always, let me know if you have any questions.